Good afternoon, ladies and gentlemen. We have one final problem in this chapter, easily the most difficult one, not only because it includes calculus, but it includes the concept of coupled equations. And if you haven't seen that before, that can really throw you for a loop if you are comparing your final answer to what's listed in the back of the book or in an instructor's manual, for example. And so I'd like to go through this problem and show you how you can conquer that type of a problem. And in this problem, we're told that we have an object of mass m that's sitting at rest in equilibrium at the origin. So, all the initial stuff for movement is 0. And then we turn on this new force at t is equal to 0 instantaneously that has these following components. And our job is to calculate the position and velocity vectors. And that's a pretty straightforward task. We would be using Newton's second law in a way that might look familiar if you've seen some of the other videos or done some similar problems. If we wanted to go from force to an acceleration, what we could do is we could divide both sides of this expression, Newton's second law, by the mass. And then, hey, we've got the force divided by m is equal to the acceleration vector. And then normally, from this point, we would integrate acceleration with respect to time to get velocity, and then integrate velocity with respect to time to get position. If this looks familiar to you, that's great, but do be warned, you can't do that straightforward in this problem on both components at the same time due to the presence of the y component of position being intertwined with the x component of force, right? So whatever happens in the y component of the position, that's influencing the x component of force, which is ultimately the x component of the acceleration as well. So we have this this kind of very intertwined, like I mentioned, juggling effect that we have to account for. And if we just integrate both components blindly, you will not arrive at the correct answer. So what I'm going to do is I'm going to delete this portion for now, and I'm going to write out what the acceleration vector is going to look like just at this first step right here. Okay? So we've taken the force vector and divided it by the mass. Excuse me. So we would ultimately have this as a vector expression. If I take k1 plus k2 times y, and I divide both of them by m, this is going to be the I hat component, and I will do the same with the other piece, k3 times t divided by m, and this will be the j hat component. That's our acceleration vector. Okay? Acceleration vector right there. And what we need to do in order to calculate the position vector and the velocity vector, both components, is we need to figure out and unravel what y is in terms of all these other variables that we have included, right? We want y in terms of k's or t or m, right? We want that in terms of some type of combination of those variables. And in order to do that, well, we'll have to start with this component of the acceleration and integrate forward. And I'll show you what I mean on a fresh page, because we're going to run out of room here pretty quickly. If I take just this component right here, I have the following. The y component of the acceleration is equal to this. We know that we can get the y component of the velocity as a function of time by integrating the y component of the acceleration with respect to time and including some kind of constant, which would be any initial velocity with respect to the x direction. Well, we're integrating this expression, k3 times t divided by m, with respect to t. And if you recall from the problem description, at the beginning of this whole scenario, the object was at rest in equilibrium, right? At rest in equilibrium at the origin. So there is no initial velocity in the x direction. So plus 0. Or you can just ignore writing anything if you like. And if you're not comfortable with integrating expressions that include kind of variables like this, you can always factor them out. So you'll have k3 divided by m, and we're just integrating, pardon me, forgot a dt there, integrating t with respect to the variable t, and that's pretty simple. That's kind of like just integrating x with respect to x. We'll have k3 over m times t squared divided by 2. And I'm actually going to kind of combine these all together and make them one expression. So k3 t squared over 2m. And that's the y component of the velocity. If we integrate this one more time, we'll have the expression for y. So let's actually maybe do that over on this side. R, the position vector, y component as a function of time, is the same as writing just y, and that's equal to integrating the y component of the velocity with respect to the variable t. And we have to include any type of constant displacement with respect to the y direction. Well, this is a similar situation to what we had on the left side here. We're going to integrate what we solved for down at the bottom, and instead of writing it, I'm just going to copy and paste it. So this right here, okay, we are just integrating this expression with respect to the variable t, and because the object was located at the origin, at the beginning of time, or the time interval, however you'd like to say it, the y coordinate was 0. Okay, so another thing that we don't have to worry about here. If you want to integrate this expression in a similar manner, like over on the left side where all the constants are factored out, you can do that this way with respect to t. There we go. And we'll be taking k3 over 2 times m multiplied by t cubed divided by 3. And if we bring this all together as a single chunk, we'll have 6m. So we have the y component for the acceleration, the y component for the velocity, and now the y component for the position. Let's perhaps start labeling these so that we can refer to them kind of in shorthand, and I don't have to keep writing this over and over. I'm going to actually start numbering these here, beginning at number 4, and you'll see why in a moment. But we'll call the acceleration vector y component equation number 4, the velocity y component equation number 5, and the y component of the position number 6. So that means now that we have equation number 6, which is y, we can go back to the x component of the acceleration and plug that in here, right? Plug that in here and do all this integration like we just did and get what the actual expression would be, the correct expression. An expression that is not in terms of y. So let's start off with what we have for y here. And let me go to a fresh page. I'm going to put that here. And the x component of the acceleration is this expression right here. So what I'm going to do is I'm going to erase what I have listed for y. I'm going to extend this out a little bit. I'm going to say, hey, here is what y was, this expression right here. It's not going to fit in there very nicely, but hopefully you'll get what I mean. This is the x component of the acceleration. Now, I'm going to simplify this a little bit. We can't keep it like this. It's very messy. What I would recommend is breaking this up into two pieces. So we'll have k1 over m plus, I'll do it this way, k2 over m multiplied by k3 t cubed over 6m. And if you'd like to bring this together even further, we'll have k2, k3, t cubed over 6m squared. That is the simplified expression for the x component of the acceleration. And to keep in line with our number system that we had before, this is going to be equation number 1 here. Let's kind of partition this side of the screen. And I'm going to do the same type of approach I did on page 2 here, where I started with the acceleration component, and then I integrated that component of the acceleration to get the velocity, and then I did it again to get that component of the position. So if I, excuse me, if I want the x component of the velocity with respect to time, I am going to integrate the x component of the acceleration with respect to the variable t, and I need to include any type of initial velocity in the x direction. Our integral is this expression right here. I'll copy and paste that one over. Okay, beautiful, beautiful. Oops, pardon me, sorry. Right there. And again, everything was at rest. There is no initial velocity in the x direction, so we'll just have a plus 0. And the integration is with respect to the variable t. Did I miss that on anything else? No, I didn't. Okay, so coming back here, we can actually split this integral into two if you're not comfortable doing it entirely as a single integral. And k1 over m is just a constant, so we are integrating really just the number 1 with respect to t, and we are adding k2, k3 divided by 6m squared times the integral of t cubed with respect to t. And the integration is pretty straightforward. We'll have k1t over m. Ooh, that's an ugly m, pardon me. Plus k2 times k3 over 6m squared times t to the fourth divided by 4. We can simplify this even further by doing k1t over m plus, let's see, k2, k3, t to the fourth. 6 times 4 is 24, so 24m squared. And this is going to be the final simplified expression for the x component of the velocity, which I'm going to label as equation number 2. Oof, a lot of work here. Okay, so one more integration on this component, and we'll have the x component of position. So let me copy this over to a fresh page, and we're saying that the x component of the position vector as a function of time, which is the same as, writing x, is equal to the integral of the x component of the velocity integrated with respect to time, and we're including any type of initial position in the x direction, which there is none. That'll just end up becoming 0. So we have integral of what I copied from here, and I will close the bracket. With respect to t, there's no initial x position, and again, very straightforward integration, k1 over m. You can chunk up the integral this way, say dt plus k2, k3 over 24m squared. All of this that I'm factoring out are constants. The only thing that we're concerned about is integrating anything that is a t, and that's with respect to dt on the integral there. So we have k1 over m times t squared over 2 plus k2 times k3 over 24m squared multiplied by t to the fifth divided by 5. A little bit simplification required here. Bringing it all together, we have k1 t squared over 2m plus k2 times k3 times t to the fifth. 5 times 24 should be 120 m squared. All right. So that would be then equation number 3. So we've done all this integration. What was the point of all this, you might ask? Why did we do this kind of weird numbering system? Why did we start with 4, 5, 6 and then 1, 2, 3? So here is what I ultimately want to display the final answer as, right? So it would be the acceleration vector is going to be, expression number 1 in the I hat direction plus expression 4 in the j hat direction. The velocity vector will be equal to expression number 2 in the I hat direction plus expression number 5 in the j hat direction, and the position vector equal to expression number 3 in the I hat direction and expression number 6 in the j hat direction. So we have 1 and 4, 2 and 5, 3 and 6. the numbers kind of line up in a way that makes sense. You know, if we started 1, 2, 3 over in the y component, you would have, 1, 2, 3 over on this side, and then 4, 5, 6 over on the left. And it may not be super apparent how we're bringing these things together. But anyways, let's fully write out what the expressions would be for the velocity vector and the acceleration vector, because that's what the problem required us to do. If we write everything out, we don't really care about what the acceleration vector is, like the full expression, but just for the sake of completion, this is what it will look like. We'll have k1 over m plus k2, k3, t cubed over 6m squared in the I hat direction plus k3 times t divided by m in the j hat direction. So that's the acceleration vector. Okay, that's fine and dandy, but the meat and potatoes of what we were after are the following two expressions. k1 times t over m plus k2 times k3 times t to the fourth divided by 24 m squared pointing in the I hat direction plus k3 t squared divided by 2m in the j hat direction, and the position vector will be k1 t squared over 2m plus k2 times k3 times t to the fifth power divided by 120 m squared, all pointing in the I hat direction, plus k3 times t cubed divided by 6m pointing in the j hat direction. So here is the final answer for this particular problem. The two vectors as a function of time for the velocity and position are what I boxed here in purple. This one and this one. That's it. Oof. 5 pages. Thanks for watching. Best of luck to you. Take care.